Hello, this is video 80 and we're going to talk about simple harmonic motion. So before we do that, let's do a quick review of Hooke's law. So what we learned about Hooke's law was that a stretch spring exerts a restoring force proportional to the stretch. And we saw this equation and we used it, and we said all it means is if you stretch a spring, for example, you stretch it to the left here, then you know the spring is going to pull back to the right. If you stretch more, then the spring is going to pull back more. So we said that the amount of force that the spring is going to exert depends on how much that we stretch or compress it. That's what the X was. And then K was the spring constant, which described the stiffness of that spring. So when you pull back on a spring, it's going to oscillate back and forth due to this restoring force. So this is a new word here. We're just saying restoring force because it's trying to bring the object back to that rest position or that equilibrium position. So now we're ready to talk about simple harmonic motion. The most simple way to describe simple harmonic motion is with this bullet here that says motion that occurs when the net force along the direction of motion obeys Hooke's law. So we just talked about Hooke's law, which described that restoring force that was proportional to that displacement. So whenever you have motion where there's a force that is causing that motion, and that force is proportional to the displacement from equilibrium, just like Hooke's law, then that motion is going to be called simple harmonic motion. And the most common example for simple harmonic motion is going to be a mass on a spring, because a mass on a spring obeys Hooke's law. Any object that obeys Hooke's law is going to move in simple harmonic motion. We see in this picture here that there's a mass that's going up and down, and as it does so, there's a scroll of paper here that is rotating and recording the motion. So you can imagine that there's a pen or some kind of marker on the mass. As it oscillates up and down, then the paper traces out the motion. And you can see the shape of this motion. The shape of this motion is sinusoidal. So it turns out that whenever something undergoes simple harmonic motion, that the motion can be described by a sinusoidal function, which is either a sine wave or a cosine wave. And we're going to use a cosine wave. Some books do it with a sine wave. It works just the same way. I just choose to use the cosine wave. So we're going to be talking about this equation very soon. But before we do, I just want to make a couple of notes. First of all, we're describing the motion of this object that is oscillating back and forth. In the past, when we've talked about motion to describe position, velocity, and acceleration, we used the kinematic equations. But now, for simple harmonic motion, we cannot use the kinematic equations. This is because the acceleration is not constant. We said we could only use the kinematic equations when the acceleration was constant. How do we know that the acceleration is not constant? Because the object is being pulled on by a force that depends on the displacements, right? It obeys Hooke's law. Well, if the force depends on the displacement, that means that the acceleration also depends on the displacement. So that's why we say it's not constant, because as the mass is moving up and down, as that displacement changes, the force changes and the acceleration changes. So before we can use this equation that we just saw in the previous slide, and I'm going to write it down here, it was the position as a function of time equals a, which was the amplitude, cosine of 2 pi ft. We talked about f being the frequency. But let's talk a tiny bit more about the frequency. For a mass on a spring, the frequencies, which we said was the number of cycles per second, is going to depend on the physical properties of that mass on a spring. So if you have a mass on a spring, you've got the m, the mass, that's going to affect the frequency. And then you also have the spring constant, k of the spring, that determines its stiffness. So this is the equation here that relates the properties of this mass on a spring to the frequency. We're not going to derive it in this class, but we just want to make sure that this equation makes sense. If we increase the spring constant, that means that we make the spring more stiff. Can you see that if it's stiffer, that the mass will oscillate faster because you're going to have more force. It's going to oscillate faster. So we can see that this makes sense. As k increases, the frequency increases. Now, on the other hand, if you increase the mass, can you see that if you make this a bigger mass, how it's going to hinder the motion and it's going to make it oscillate slower? So increasing the mass makes the frequency smaller, so it makes sense that the mass is in the denominator. An important thing to note about this equation, and we'll be using it in just a few slides, we'll practice with that, but an important thing to note right now is that the frequency, so how many cycles per second when this mass is oscillating, is independent of the amplitude. Remember, the amplitude is that displacement from equilibrium. So how far you're going to stretch it from equilibrium. Let's say you pull it this much, and that's the amplitude. You might think that the more that you pull it from the equilibrium position, the bigger the amplitude, the faster it's going to oscillate. But this equation shows us that amplitude does not come into play for the frequency. Let's do a question. A mass oscillates on a horizontal spring with period t equals 2 seconds. If the amplitude of the oscillation is doubled, then what's going to happen to the period? So how long is it going to take to oscillate if you double the amplitude? So let's just visualize this. By now you know I'm a visual person. I've got to see things. So this is the position of your mass at the equilibrium position. And then let's say that originally it's going to oscillate because it was stretched by this much. This was the amplitude. So it's going to oscillate back and forth up to here, to the left, and back to the right. It's going to oscillate back and forth. How long does it take for a complete cycle? Now, what we're saying in this question is that now you're doubling the amplitude. So you stretch it all the way up to here. The amplitude is twice as much. So that means it's going to go back twice as much on the left side as well. So we just learned that the frequency, right, the number of oscillations per second, was independent of the amplitude. The frequency was equal to 1 over 2 pi times the square root of k over m. Had nothing to do with the amplitude. Well, if the frequency has nothing to do with the amplitude, then that means that the period has nothing to do with the amplitude as well, because the period was equal to 1 over frequency. So it doesn't matter the amplitude, it's not going to affect the period, the time for a complete cycle.